Hey, good day, everybody. We are here now working on section 5.2, the binomial probability distribution. As we work through this today, we're going to focus on the definition and notation, and then how we can find binomial probabilities. And then once we get those things down, we're going to look at examples from statistics, using formula and using a calculator to be able to solve some problems. So let's get ready and get started. So a binomial probability distribution function is, number one, it's a discrete distribution function. So it's just like section 5.1 in the sense that we're going to have random variables assigned, and then we're going to have a probability of the random variables. Now, just so you know, later in this section, and I do expect you to read through it as well, but in the section, they will talk about why the way we're going to assign probabilities is the way it happens. But basically, it comes from the binomial theorem in algebra, something all of us probably learned or were supposed to learn in Algebra 2 or pre-calculus. And if you remember that the binomial theorem was connected to Pascal's triangle. So it's actually, there's kind of a lot of cool stuff. Pascal's triangle looked like this. You might remember seeing these kinds of numbers, and it would go on and on. And they would give you coefficients of polynomials. Well, it turns out they're actually combinations. And the binomial probability distribution will make a table just like this that we saw in section 5.1. So there are four characteristics we need to pay attention to here. The first one is to know if you have a binomial probability distribution, you have what's called n, or usually it's labeled small n, but a fixed number of trials. So, for instance, a good example would be a basketball player shooting free throws. If the basketball player goes to the line and say, he's fouled 5 times and he got 10 free throws, then he would have 10 trials, all right? Because he would shoot those free throws, and he's either going to make or miss the free throw. So it's a fixed number of trials, all right? Think about that. If you think of the Olympics and archery, they'll, or shooting bullets at targets, they have a certain number of shots, and then those will be a fixed number of trials. Now, number 2, the trials that occur must be independent. In other words, whatever happens on one trial is not going to affect the outcome of the next trial or the previous trials. So the trials are independent, okay? There are only 2 outcomes of each trial. 2 outcomes. Generally, we call those outcomes a success, or we call them a failure. All right? That's generally. And so, for instance, if you're shooting free throws, a success would be you made the free throw. A failure would be you missed the free throw. If you were in a shooting competition with archery or guns in the Olympics competition, then you either hit the target or you miss the target, success or failure. So hit or miss, on or off, 1 or 0, success, failure. Think 2 outcomes and 2 outcomes only. And a success doesn't necessarily have to be something good. So, for instance, you could, if you were a manufacturer, a success could be, you could consider a success, the small probability that the product that your machine stamped out was not a good product, so it was defective. So a defective would be considered success, and a non-defective a failure, which means the bad product is a success and the good product is a failure. So we label these not to categorize anything specifically, but just to give us which one's going to be the probability of success. Okay? And then finally, the last thing, because the trials are independent, the probability of a success is the same for each trial. So if you're Stephen Curry shooting free throws, he hits 90% of his free throws, so the probability of success is 90% on any free throw that he shoots. Okay? If you're flipping a coin, the probability of getting a heads success is 5% or 50%, right? On every flip of the coin. It's always 50%. Okay? So you have to keep these things in mind to remember that. Now we have some notation that goes with that, okay? Very often we let S stand for the probability of a success, and we let F stand for the probability of a failure. Now, using our earlier notation, we would say probability of success and probability of failure, and that would be very typical probability notation. But probability of success from now on will be called P, and probability of failure will be called Q. All right? And Q, just so you know, is always the complement of P, so it's 1 minus P. All right? And so this is the notation we use to refer to probability in binomial distributions, okay? And this will be very important later on in subsequent chapters, so keep this in mind. N, it always stands for the number of trials, okay? X stands for the specific number of successes. In other words, this is the random variable. Okay. And the probability of X, then, that stands for the probability of X successes. Probability of X successes. Okay? And so that's our notation that we're going to use here. All right? The one thing you want to really make sure of is that the X probability, the random variable, is associated with the probability of success. Okay? So when you're talking about an individual success and the probability of X successes, that's going to be related to the value of P. So you want to keep that in mind. That's a fairly important thing. Okay, let's move on. So the first thing we have to do is we have to decide, is the following a binomial probability distribution? And what we're looking at are page 227 in the textbook, problems 5 through 12. There are some examples there. And so I will pick a couple. So let's do number 5, first of all. So here's number 5, sort of abbreviated. We got a survey of 3,930 subjects, and the age of the respondents is recorded. Okay? So let's think about this. Number 1, do we have a fixed number of trials? And the answer is, sorry, I got interrupted by a message on my phone. So the number of trials is going to equal what? 3,930, because we're going to ask that many different people, and they're individual. And what one person says their age is different from the other. And so we have the number of trials. Number 2, we know these are independent because whatever your age is not going to affect what my age is. So we're pretty good there. But problem 3, we have an issue. There are more, or potentially more than 2 outcomes. Because they're just giving their ages, their age could range from 0 to, what's the oldest person? 120. It could range anywhere, any of those age values. And so this would not be a binomial distribution. And now, when this is presented as a multiple choice question that you answer just yes and no, one of the things you need to do in this sort of online environment is make sure you go through this thinking and write it down so that you definitely understand. All right. Now, I can stop right here, or I could check number 4. There's a problem with number 4 because the probability of getting, say, age 16 and the probability of getting age 30 might be different. So you could say the probability of A would not necessarily be equal to the probability of B if A and B are different ages, because you might have, 50 16-year-olds in the group and 100 30-year-olds. And so you don't know. So they're not going to be likely not the same. All right. And so because of that, it's not a binomial distribution. Okay. And so you need to think through that. So let's go to problem 6. And so on problem 6, we have the same survey of 3,930 respondents, okay? And they are asked whether they have fired a gun. And they only need to answer yes or no. All right? So that's the next problem. Okay? So now we go through it. Number 1. Again, we have n equals 3,930 trials. Okay? They're independent. Whether I have fired a gun and you have not, that doesn't affect one way or the other. So we can see that these are independent. And number 3, are there more than 2 outcomes? And the answer is no. There are exactly 2 outcomes. They are yes and no. And you could call yes a success and no a failure, or vice versa. It doesn't really matter. And so there are exactly 2 outcomes. And when you think about the probability, when a person answers this question, they have a 50% chance of answering it yes, or a 50% chance of answering it no. Because this is like a coin flip with 2 choices, right? Now, of course, if they live in Montana, maybe they've got an 80% chance of answering it yes and 20 no. But all things considered, this is a 50-50. So the probability of success is equal to 50%, and the probability of failure is 50%. And so we could say that, yes, this is a binomial distribution. Okay? Now, notice here the probability of success applies to the individual trial. Okay? And that means that, if a person's going to answer the question and it's 50% one way or 50% the other, you don't know which. And so in a random situation, now this could change, and there are some fudgy things you could do on this to make it a no. But in general, I would say that one's a yes. So hopefully you get a better feel for how this works. There's one other thing I want to show you about this that I think is fairly important, and that is this. Once you get a binomial experiment like this one down here, then you could make a distribution table for this. So your random variable would be the number of respondents who, let's say the success is shooting a gun, answered yes to shooting a gun. And so you have to ask yourself, what number of respondents answered yes? Well, 0 could have, or just 1, or 2, or 3. And this table could go all the way, one number at a time, to 3930, where they all answered yes. Then you would find the probability, based on this 50-50 scenario, of that 0 people would answer yes, or that 1 person or 2 person. And this is where you would use a formula to fill these in, okay? Or technology. And so you can create a binomial distribution table, all right? So that's something I want you to keep in mind. And we're not going to do ones this big, okay? We'll do some a little smaller. So I have a picture here of table A1 from our textbook. It's on page 731 in your textbook. And this table is a binomial PDF table. Okay? It is the binomial PDF table. And it shows us for up to n's of size 8, so n from 2 to 8, some various tables for different probability values, okay? So let's change that problem up a little bit. Suppose we interview n equals 6 people, okay? And suppose they answer yes or no, whether they have fired a gun. And we know that the probability of success is 0.5, okay? Then all we have to do is we can go to this table and we can find n equals 6 and the probability equals 0.5, and we go down the probability and across the 6, and that gives us a number for having 0 successes. So if we were making this table, X is the number of successes. Since there are 6 people, 0 could have fired a gun, or 1, or 2, or 3, or 4, or 5, or 6. okay? And then the probability of 0 people would be 0.1016. That's what we got right there. And so if we had 1 success or 2 successes or 3, all the way up to 6 successes, that would be all these probabilities right there. So 0.094, 0.234, 0.312, 0.234, 0.094, 0.016. And this would be a discrete probability distribution. And if you look at it closely, is it really a discrete distribution? Well, what we see is that we have the random variables. All our probabilities are less than 1. Do they add up to 1? Well, these two add up to 0.110, and those do 0.110. And then I have a 0.234 and a 0.234, which is 0.468. And then I have the 0.312, and that gives me 0, carrier 1, 0, carrier 1, 0, carrier 1. It adds up to 1. So this is a discrete probability distribution. So it fits all the things we've talked about up to now. And if I want to know the probability, if I want to find the probability that exactly two people shot a gun, I can find that probability, and it's equal to 0.234. Okay? If I want to find the probability that from 2 to 4 people shot a gun, that would equal all 3 of these. So 0.234 plus 0.312 plus 0.234. Okay? And whatever that's equal to, which I think is 0.780. All right? And so you can see, you can start to play the probability question game once you have the given table. And this table here helps us do it. But there's a problem with this table, and we want to look at what that problem is. The problem is it only goes up to n equals 8. Only goes up to n equals 8. And so the question becomes, what do we do if our number of trials is larger than 8? What do we do? And this is where formulas and technology become our helper. All right? So let's look at the formulas for the binomial theorem. And so here is the formula for x successes. So now, what if I was doing that last problem and I said n had 10 trials? Okay, but again, our probability of success was 0.5. Probability of failure is then 1 minus 0.5 or 0.5. And x, let's say, was equal to 3 successes. Okay, 3 people said they could shoot a gun out of the 10. Well, then we would say the probability of 3 successes is equal to n factorial, 10 factorial, over 10 minus 3 factorial times 3 factorial. So those are the n and x's, times the probability of success, 0.5 cubed, and then the probability of failure, 0.5 to the 7th. N minus x is 7. And so we would figure this out. 10 factorial, if you wish, is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 10 minus 3 is 7, so that is 7, 6, 5, 4, 3, 2, 1. And 3 factorial is 3 times 2 times 1. And then you have 0.5 cubed times 0.5 to the 7th. And when these are not equal to 1/2, like say it was equal to 1/3 and 2/3, you can see these will be a little different. Now, at this point, it's a calculator problem. But you can see if you're doing this using these formulas, you have some nice canceling, and then the 3 cancels with the 9, and the 2 cancels with the 8. And so you really have 10 times 3, 30 times 4, which is 120. And then all you have to do is use your calculator to figure these animals out right here. Now, as you can see, I typed this into my calculator right here, right there. 120 times 0.5 cubed times 0.5 to the 7th. And I got 0.1172 as the probability. And so you can use your calculator after writing out the formula. You can use your calculator to do that. Now, you'll notice by hand I simplified factorials. But what if the numbers get big? Well, then much bigger than 10, then these simplifyings become much more difficult. So can you do the factorials as well? And the answer is yes. On your calculator, you need to go to the math menu. Excuse me, I'm doing this right now just to remember. But you go to the math menu, and under the math menu, factorials, I believe, yes, factorials are under the math menu and the probability. So you would look for the math menu down here on the calculator. Let me move this up. Here's the math menu. And then you would arrow over to the probability menu, and you will see the factorial there. You can use that, and then you could take 10 factorial divided by, and then put in parentheses 7 factorial times 3 factorial. Now, why do you have to put it in parentheses? Because of order of operations. You have to figure out the whole denominator and then do the division, okay? Because there's something in the denominator, you have to do that first. So grouping things are first. So fractions cause grouping. So you can do that. And then that will help you figure this part out, okay? Or you can use the key also under probability called NCR, which is a combination. It turns out this part of the formula is a combination. And so if I were, instead of typing what I did there, if I typed 10 NCR key 3, which is 10 things taken 3 at a time, and then I multiplied that by 0.5 cubed times 0.5 to the 7th, then this, and I could put parentheses there if I want, then this will also give me the answer. Now, I suggest you find your best strategy, the one you can do, and that you know how to do, and you type it correctly, and if you get this answer, then you know how to do it. If you don't, get some help. All right? Learning how to use the calculator is pretty important at this point. Okay, so let's go to, I'm going to post a video now that shows you how to use the calculator and the statistics functions to actually find this number. Okay, 0.1172. All right. Here we go with shaky video calculator again. Hopefully this will help. So I want to show you how to find these probabilities using your calculator, but not the formula. The formula is actually built into the calculator under this menu here called distribution. So to access a blue menu, whoops, hit a couple of things there. You hit second vars, and that gives you the distribution menu. And if you scroll down to the distribution menu to A and B, you will see a couple of binomial probability distribution function menus. Now, A is the binomial probability distribution, and B is the binomial cumulative probability distribution function. Now, do you remember what cumulative is? It adds everything from the first random variable up to a certain point. Okay, so knowing which one of these to use is really important. But for the problem we were doing, we want to use the binomial probability distribution. And so our n was 10. And there we go. Our n was 10, our probability of success was 0.5, and the x value I wanted was 3 successes. 3 people that said they had shot a gun. So once I type that in, I can press enter, and you will notice that I get the same probability that I got from before, 0.1172. So now you know the methods of finding the probabilities, okay? Using the table if they're small, but once they're bigger, you can use the calculator or the formula. There are a couple other formulas we need for binomial distributions, and the first one is what is the mean? All right, so the mean of a binomial probability distribution is n times p. Okay, so for our example, it would have been 10 times 0.5 or just 5. That would have been the mean. All right, the variance, which is sigma squared, is equal to npq, or 10 times 0.5 times 0.5, since success and failure have the same probability. And that would be equal to 2.5 in this case. And therefore, pardon me, the standard deviation, sigma, would be the square root of that, square root of npq, which would then be, in this case, the square root of 2.5, which is approximately 1.57 or so, something like that. All right, and you can check that on a calculator. Okay, now, in terms of statistics questions, we like to use our range rule of thumb, which says that values are significantly low if they are less than the mean minus 2 standard deviations. They're significantly high if they're greater than the mean plus 2 standard deviations. And they're not significant if they're in between. All right, in between is not significant. Okay, now this rule hasn't changed for any situation. We keep using this kind of rule. So let's look at one more problem, and then I'll close this video. I expect you to read through the text, practice things. If you have questions, please send me questions, okay? But let's go through a couple of problems and help you get a better sense of this. Okay, this problem set is on page 228 in your textbook. And so we want to use it to kind of go through how to do this. So notice they say 40% of consumers believe cash will be obsolete in 20 years based on a survey. In each of the exercise, assume that 8 customers are randomly selected. Find the indicated probabilities. Okay? So, number 15 says, find the probability that exactly 6 of the selected customers believe cash will be obsolete. So they want me to find the probability that X equals 6. That's what they want me to find. So that's exactly one element. Now, if you think about this, we could use the table, right? Because n equals 8. And then from the table, we could go to where x equals 6, and we would look for the probability equal 0.4, and we would go down and across and find the number. So that would be one way to do it, okay? We could also set this up by formula, all right? The formula, again, was n factorial over 8 minus 6 factorial, 6 factorial, times the probability of success to the 6th power, times the probability of failure, which is now 0.6, to the 2nd power. All right? And so that formula would give us this answer right there. Or we can just use the calculator, which would be binomial PDF, where n was 8, the probability of success was 0.4, and the number of successes was 6. And so the calculator would give us a solution in that way. All right? Now, I want you to go through, and I'd like for you to do that. I'm just going to punch it up on my calculator and do it myself as well. And however you did it, you should have got that the probability was equal to 0.0413 if you round it off. All right? Fair enough? So about 4% chance of 6 of the customers believing cash will be obsolete. All right? Now, the next question changes this. It says, find the probability that at least 6. So 16, find the probability that x is greater than or equal to 6. Okay? Greater than or equal to 6. So how do we do that one? Well, one way to do it is some students would say, oh, well, that's the probability that x equals 6 plus the probability that x equals 7 plus the probability that x equals 8. And they would just add those 3 up. And so they would get 3 values from the table. or they'd do the formula 3 times, or they'd use the calculator 3 times. And all of those would work. And so what I'm saying to you guys is that we could do this on the calculator using what is called the binomial CDF, the cumulative distribution function. And so how would we use the cumulative distribution function? Because it asks for the same thing. It asks for n, p, and then it asks for an x value. But we have 3x values. So how does cumulative work? Well, if you go back to frequency tables, here's what our frequency table from this table here would look like. 0, 1, 2, 3, 4, 5, 6, 7, 8. We could have all those numbers of successes, and then the probability of x, and then we got a probability listed for each one of these. In fact, we know the 6th one, it's 0.0413, and I don't have the others right now, but that's okay. But how does a cumulative distribution function work? Do you remember how it worked, a cumulative frequency table? We actually add them up as we go. So the first one lists a 0, but the second one lists the probability of 0 plus the probability of 1. And the third and the 2 lists the probability of 0 plus the probability of 1 plus the probability of 2. So the cumulative distribution function adds from the bottom up, but we want the answer from the middle to the top. So what we have to do is think of this as a complement to use our calculator. And so here, instead of saying the probability of x is greater than or equal to 6, we say it's 1 minus the probability that it's less than or equal to 5, which means we're going to accumulate all of this up to 5, add those up, and then subtract that from 1, and that should give me what's on the top. And that's how the binomial CDF works. So this is exactly the binomial CDF, and I would put 8.4, and x I would put 5, because I'm only going to add it up to 5. And so I'm going to do this on my calculator right now, and this tells me that the probability of 6 or greater is 0.1238. Okay? Whoops, excuse me, I had the wrong function. I had PDF. So you've got to make sure you type in the right one. So 8, 0.4, 5. Sorry, I did that. And so, okay, I need 1 minus this, so I'm going to have 1 minus 0.9501, which is equal to 0.0499. And that makes sense, because the probability of 6 is 0.041, and these are going to be even rarer, so they'll be smaller, and so just a little less than 5%. Okay? So it's 1 minus the binomial CDF. That's how you can use it and do it on a calculator. And you really want to think about this CDF thing, because we're going to use it for normal and for other situations, and how it adds from the bottom up. But it makes the calculator really a slick way to use it. Okay, let's see if there are some other ones here. Let's go to this problem. Number 17 says, find the probability that fewer than 3 of the customers believe that cash will be obsolete. Okay, So fewer than 3. So let's work on that one. So 17. The probability that the random variable is less than 3. Now, in the binomial distribution, less than 3 actually means less than or equal to 2, right? And that's because it's discrete. Since it's less than 3, it can't be 2, so it's less than or equal to 2. So now that we have that value, okay, this is a binomial CDF. It's accumulating on the bottom part of the table. It's just the 0, 1, 2 probabilities added together. Now you can find 0, 1, 2 separately and add them. You could use the table because this one fits the table. But we would like to use the binomial CDF. And in this case, since it's just the less than, it's not the greater than, I don't have to subtract it from 1. So I would do 8.4, and I want to add them all up to 2. And so that would be how I do this. And punching that on my calculator, I get 0.3154 for my probability. Okay, now you can check this by doing the table if you're doing it. Because n was 8, you might use the table. It's probably the fastest way to do it. But are you starting to see how these problems work? Okay. Now it says, find the probability that no more than 3 of the customers believe cash will be obsolete. No more than 3. Okay, so what's that one? Probability of no more than 3. Probability that X is not greater than 3. Which means, or no more than 3 means less than or equal to 3, right? Because it can go up to 3, but then it's no more than that. So this one is very similar to this, except that we can use the binomial CDF, and we can just go up to 3. All right. Now, how do I get this so quickly? I find it helpful to think of it being in a table. 0, 1, 2, 3. No more than 3 means I got to add all those probabilities. And so by thinking of it in the table, that helps me use the statement correctly. Okay, so those are kind of the variations that you're going to encounter. You could find in between, so then you might add them up. Now, this problem was a little easier because n was equal to 8, but I stuck with showing you the calculator because that's probably the newest way, and slightly more difficult to understand how it works. But it's the best way to do problems where n is bigger than 8. Okay. I want to look at problem 30 as well, which is on page 229. And in this one, they have a group of n equals 16 couples. All right. And all of those couples used a method to get predictions of whether they were going to have a girl or a boy, where the probability of success of having a girl is equal to 0.5. Okay. And if the method had no effect, that would be the probability. All right? So all they want us to do first in these problems is they want us to find the mean. and the standard deviation. So what's the mean? Well, the mean is equal to NP. So in this case, it would be 16 times 0.5, or 8. And the standard deviation, sigma, is equal to the square root of NPQ, which is equal to the square root of 16 times 0.5 times 0.5, which is equal to square root of 4, which is 2. All right? So we can find the mean and standard deviation. And then they want us in part B to use the range rule of thumb to find the values where significantly low and significantly high happen. So what we need is we need the mean plus 2 standard deviations. This is significantly high, so 8 plus 2 times 2 would be 12. And the mean minus 2 standard deviations is 8 minus 2 times 2, which is 4. All right? And then they ask us, so you're going to be significantly high if 12 of them using this pregnancy technique had girls. You'll be significantly low if 12 of them using this pregnancy technique had, only 4 of them had girls, all right? And so, if you were 12 or above, that's significantly high, and 4 or below, that's significantly low. So the last question asks this. The result is X equals 11 of them were girls. Is that significantly high? Okay. And so is it significantly high? And the answer is no, since 11 is less than 12. All right? So in order for it to be significantly high, it would have had to have been greater than 12. So what does this suggest about the method of the effectiveness of the method of trying to predict the gender of your child? What it suggests is that the method has no effect. So remember, if it's rare, significantly high or low, then there might be some effect. But if it's not rare, it's going to fall in the normal range, okay? And so that's kind of the last question. So hopefully you enjoyed that. Hopefully this will help you as you read through the section and start working on the problems. Please ask questions in email or a text message if you have any. I'll be doing chapter 6 videos probably tomorrow. I'll start one of those. Alrighty? Bye.